Here's our voice memo recorder. We've got it plugged into a speaker. It's running off of 5 volts. Let's take a look at how it operates. So we've got our LED display here. We've got our control push button here, microphone, amplifier, and volume control over here. There's only one button. Our LCD shows us what our choices are. Right now, there's no recorded voice, so our LED is off. If we hold out the button and release it, we get an error message saying there's nothing to play because right now the memory is empty. Here's our 32 by 8 static RAM that's controlled by SPI. If we hold down the button for more than a second, the green light will come on and we'll be able to record a message. Remember to buy milk. When we release the button, the LED flashes to let us know there's a message. The LED went out when we released the button, but it also would have gone out had we run out of memory. With 32K, a 10 kilohertz sampling rate, we have a little over 3 seconds worth of recording. To hear our message, we just press the button and release. Remember to buy milk. If we want to erase the message, we press the button while we're playing. And the light goes out to let us know there's no longer a message, there's nothing to play, and if we try to play, we get an error message saying there's nothing to play. So it's a pretty simple user interface. There's a finite state machine that knows what state we're in, whether we're waiting to play a message, whether we're waiting to record a message. When we press down the button, it times how many states the button is down. Once it's down a second, it goes into recording mode. If it's released before a second, it starts to play. If there's no play, it goes to an error message. So there's just a few states that are in there. All the hard work is actually done in a timer interrupt. There's an internal timer set up to interrupt every 100 microseconds or 10 kilohertz. Every time an interrupt occurs, the interrupt service routine either does nothing if we're sitting there idle as we are now. It reads the internal analog to digital converter if we're recording and stores the value into the SPI RAM, or if we're playback, it reads a value out of the SPI RAM and plays it through the digital to analog converter to the speaker. We use the SPI RAM in its sequential mode, so in recording, we just send 1 byte to the RAM every time a new byte comes in, and it gets loaded into the next sequential memory address. When we play, similarly, we use sequential mode so that when we read a byte out of the RAM, it goes to the DAC, and the next time we read a byte out of the RAM, it comes from the next sequential mode. All we really need to do in the interrupt service routine is keep track of what the maximum amount of bytes we can write to the RAM is, how many we've written so far, to make sure we're not at the end of RAM, and we're reading to see how many bytes were stored, and read until we hit the end of storage. The foreground program, the finite state machine, is still looking to see what the user is doing, and if the user presses the button, for example, during playback, it sets a flag. The interrupt service routine sees that flag. It marks the recording as erased, basically by saying there's 0 bytes stored. They're not actually erased from the RAM, and we go back to not having a recording. In the foreground program, if we make a recording, remember to buy milk, the foreground program sees that there's more than 0 bytes stored and goes into a mode where it flashes the LED on and off. Here we have a block diagram of our system. The large rounded rectangle is the microcontroller that has most of the things we need to implement the voice recorder. We need to add an external microphone. In this case, we're using an amplified electret microphone from Adafruit. You could buy one from SparkFun that works as well. And in fact, in Lab 7, we built our own, which would work. It puts out a 0 to 3.3 volt output, which goes into the internal analog multiplexer of the Cortex M0. The analog multiplexer allows us to use almost any of the pins on the microcontroller as analog input. To the ADC, in this casing, we're using analog input 4, which is connected to Arduino pin A3. In the first microcontroller lab, we used port I/O to blink an LED. We're going to use that LED here to let the user know either there's no recording, they're recording, or that a recording is available. In the second microcontroller lab, we added a push button connected to ground, and we used the port I/O's ability to pull either up or down so that we didn't have to use an external resistor. In this case, we're using a pull up to know when the push button is pressed to control recording, erasing, and playback. In the third microcontroller lab, we programmed the internal DAC so that we could output a 0 to 1 volt signal that went into a 3 to 1 divider to create the signal that went into our power amp and played our speaker, and that allows us to play the output of the voice recorder on the speaker. In the fourth microcontroller lab, we programmed the timer counter to generate interrupts at regular intervals. There we varied how often the interrupt occurred to vary the frequency of the sine wave we output to the DAC. In this design, we're going to use a constant 100 microsecond, which is to say 10 kilohertz interrupt, to collect data from the microphone at 10 kilohertz and output it to the DAC at 10 kilohertz. 10 kilohertz is high enough that we can get reasonable, basically telephone audio quality. In our most recent lab, Lab 5, we programmed the serial communications peripheral, the SERCOM1, to output SPI protocol to a LCD display. The SERCOMs can do either SPI, I2C, or UART. We picked SPI because not only is it the easiest to program, but it's also the easiest to see on an oscilloscope. In the worked example, we converted our polled SERCOM design to an interrupt-driven SERCOM design, which is what we're using here. The polled design would work just as well. And finally, in the worked example, we connected a 32K by 8 SPI static RAM to another SERCOM, in this case SERCOM 0. Now, the reason we needed to use two SERCOMs is that the LCD is really pretty slow. You can't run the SPI faster than about 50 kilohertz clock. And if we ran the SPI RAM at 50 kilohertz, we wouldn't be able to store and retrieve data fast enough that we could collect data at 10 kilohertz. So SERCOM 1 is running at about 5 kilohertz, and SERCOM 0, which is running the RAM, is running at about a megahertz. Our analog to digital converter is converting our 0 to 3.3 volt microphone output to an 8-bit value. Now the ADC can convert either 8, 10, or 12-bit. We chose 8 because that's what we're storing in our RAM. If we had stored more, we'd have to use 2 bytes of the RAM for every voice sample. That would halve our recording time. As it is at 10 kilohertz, with 32K, we get 3.2 something seconds worth of recording. The way the system works is there is a front end FSM, and that's the while loop that you think of in Arduino, the main loop, and that is monitoring the button, controlling the LED, and telling the interrupt service routine what to do. The interrupt service routine is doing all the data acquisition. So the finite state machine sits in an idle state, waiting for the button to be pressed. When the button is pressed, the finite state machine begins timing how long the button is down. If the button is down for at least 1 second, it flags the timer counter interrupt to begin recording. It does that by writing the first byte to the SPI RAM, which has been set up to write into sequential mode. Once we've written the first byte, passing it an address, in this case 0, and the command write, all we do is continue to send bytes to the RAM, and they get stored in sequential locations. So to start recording, we set the number of bytes we've written to the RAM to 1, and a variable that says how many bytes are in the RAM is set to 0. That flags we're recording. The timer counter then collects the first byte from the ADC, writes it out to the RAM, and then exits after clearing the interrupt. When the next interrupt comes along, it does the same thing. There's a flag that the foreground can set that tells the timer counter to stop, and that's how the timer counter knows when to stop recording. When we release the button, the timer counter sees that flag set by the foreground, stops recording. The timer counter interrupt also stops when it runs out of memory. So either when the button's released or when we hit 32,000 samples. The foreground program goes to the idle mode when the button is released. However, now that the count of stored bytes in the RAM is no longer 0, it knows to flash the LED at a half-second rate, and it does that by counting state cycles. When we press the button and release it in less than a second, there's two possible things that can happen. The foreground program can notice that there's no data stored in the RAM, which means we don't have a recording to play. It then puts up an error message on the LCD display, waits about a second, and then goes back to the idle mode. On the other hand, if there's something to output, it reads the first byte from the static RAM by sending a command that's a read command, sending an address that's 0, and reading the first data value. It then sets the count read, which is the same as the count written, same variable, to 1. The timer counter sees that that is 1 and also sees that there's more than 0 bytes in the RAM, so it knows it's in read mode, and it proceeds to read sequentially from the ADC every interrupt, and it proceeds to read data from the RAM, 1 byte each interrupt, and output it to the DAC. Meanwhile, the foreground program monitors the button. If during playground the button is set, it resets the count of bytes to play back in the timer counter interrupt to 0, which effectively says there is no longer any recording, and that stops playback. Let's take a look at the code. We're not going into too much detail, but we should see how it's structured. The nice thing about this design is that it uses every peripheral that we've looked at since we started the microcontroller section, and most of the code, except for the finite state machine that runs the voice recorder that creates the application, hasn't changed much. Our system timer and delay function hasn't changed at all. We use the delay function to create the finite state machine clock. Our analog to digital converter is almost identical to the analog digital converter we used in the theremin. The only changes are that we only collect 8 bits, and we no longer have to be able to change from one mux multiplexer input to another, so we have it hardwired to analog input 4, the one that has the microphone connected to it. Our DAC is identical to the DAC that we've been using since Lab 3. No change there. Our SPI on SEERCOM 1 hasn't changed any from Lab 5. It just allows us to output messages onto the LCD. We're using the interrupt-driven version that we showed in the worked example, but as I said before, the polled version works just as fine. Now, our SEERCOM 0 that controls the SPI RAM is exactly the same as the one we used in the worked example, and in particular, the interrupt service uses the send byte routine and the get byte routine, send byte to record and get byte to playback. Those are fairly short, so the interrupt service does not spend a lot of time in interrupt service. And in fact, most of the time in interrupt service is spent when we're collecting data from the analog to digital converter. During idle, the interrupt service takes about less than a microsecond, and then it takes about 16 microseconds during playback and 30-some microseconds during record. We have to make sure that our interrupt service takes less than 100 microseconds because we're trying to run at a 10 megahertz rate. Here's our LED and push button. Those are the same as they've always been. We abstract those so that even though both the LED and the push button are active low, the push button returns true when it's pressed, false when it's released, and we can turn the LED on with true and off with false. We also have a function that allows us to toggle the LED because for the blink, we don't care what the current state is. Finally, we have our timer counter interrupt, timer counter 4. This is identical to the timer counter we used to output sine waves, with only the change that we no longer output the waveform, the timer counter frequency, on one of the I/O pins. The reason we did that is we needed that I/O pin for another use. If we come down and look at the timer counter interrupt, we will see that that's quite different. So the timer counter interrupt has two functions, to record and play back. When we enter the timer counter interrupt, we look at several variables. Those variables are flags from the foreground program to the background program, the interrupt service routine, what to do. If both the sample counter, which is the current count as we either record or play back, and the sample count, which is the number of bytes in the RAM when we play back, are 0, it means we're in the idle mode. The timer counter interrupt just returns, does almost nothing. If the count of bytes is 0, but the counter is greater than 0, that means we're recording. So we fetch an ADC value and we send it out to the RAM. Then we have to see if we're done. We're done either if we've run out of memory, the sample counter has hit the last location in memory, or the flag from the background to the foreground that the button's been released has been set, the stop recording flag. We then copy the number of bytes that we've recorded from the sample counter into the count, and we set the sample counter to 0. That does two things. With the sample counter 0, it means the interrupt service routine goes back to idle, and setting the count to the number of bytes allows us to play back, and it lets the idle routine know it has to flash the LED. On the other hand, if we come into the interrupt handler and the counter is 1 or greater, that means we've read 1 or more bytes out of the RAM. We're going to get the next byte and send it to the DAC. Since the DAC is a 12-bit device, but we're reading 8 bits out of the RAM, we need to left shift that data by 2 bits. The lower bits go to 0, they don't do anything. We need to count how many bytes we've sent to the DAC. We compare that with the number of bytes in this particular sample. So if the number we have sent reaches the number that have been saved, we're done. We turn off playback and we exit. Now, how does a recording get deleted? There doesn't seem to be anything obvious here. What happens is the foreground program sets the sample count to 0. If this happens, we go to the idle mode. Since the sample count has been set to 0, it also means there's no recording. Finally, let's take a look at the finite state machine. Here's our main routine. We have a number of states, probably more than we need. One of the problems we have is that if we were to be in a state multiple times writing data to the liquid crystal display, it would flash. So we have some states that we only go through one cycle to output data to the finite state machine. As usual, we start out with a bunch of initializations. We initialize all our peripherals, the two SPI, SEERCOMs, port I/O, the analog to digital converter, the digital to analog converter, and the timer counter. We set the SPI RAM to sequential mode. We only need to do that once. We set our timer counter to the 48 megahertz clock that it's counting divided by 10,000. That turns into an interrupt at 10 kilohertz. We then set up the LCD and we go into the FSM, which runs forever. The FSM starts out with an idle state, waits for a button press. If the number of bytes stored in the RAM is more than 0, we blink the LED, otherwise we don't. When the button gets pressed, we turn the LED off. We put out a message telling the user to hold the button to record or release it to play. And we go to a new state called button down. In this state, there's two things that can happen. Either the button can be held for more than 1 second, in which case we go to a record state, or it can be released, in which case we're being asked to play. However, if the number of bytes in the RAM is 0, there's nothing to play, so we put up an error message, and we go to a state that just delays for a second so the user can see the error message. If they hold the button for more than a second, we turn the LED on to let them know they can record. We enable the RAM chip select. That's our SPI signal that tells the RAM it needs to start listening to commands, and we send it a write command to write the first byte out at location 0 because we want our interrupt service routine to be able to write single bytes to it to do sequential write. Clearly we don't want to stop yet, so we make sure our flag is clear. We tell the ISR to record by setting the sample count, the number of bytes stored in the RAM, to 0. We set the counter to 1. That tells it to begin. And we jump to our record. In our record state, all we do is wait for our button to be released. When the button's released, we return to the idle state. The LED is turned off by the interrupt service routine when it stops, either because the button is released or because it runs out of memory. If we're going to play, we put up a message. Once again, we enable the SPI RAM. By the way, the chip select is cleared by the interrupt service routine whenever it stops reading or writing at the end of playback or record. We read the first byte. We set the sample counter to 1. That tells the background it should start doing something. And since the samp count, CNT, is not 0, it knows it's supposed to play back. We then go into a routine where we wait to see if the button gets pressed. If the button gets pressed, that means we want to erase. Otherwise, we wait for the sample counter to go to 0. The background interrupt service routine sets that to 0 when it's done playing, which tells us that we're done playing and we can go back to the idle mode. If we want to erase the recording, we set both the counter and the count to 0. The count is the number of bytes in RAM. When we set it to 0, that effectively says there's nothing in there. We don't actually delete the data that's in the RAM. And we go to a routine that does nothing but wait for the button to be released. Once we've erased it, if we didn't go to this state and went to idle, the button would still be down. When we released it, the idle state would think we were trying to play, but since we had just erased the data, it would give us an error message, and that would be confusing. So the only purpose of the erase state, wait state, is to wait until the button's released. Erase delay state waits a second just to allow the person using it to see the error message. Now, all these timing, like the timing, how long you display the error message and how long you wait for the button to press, are based on the state cycle. Since the interrupt service is doing all the critical timing, the cycle time for our finite state machine just has to be fast enough for a human to not feel that it's lagging. I use 100 milliseconds, and if we go back up to the beginning, you can see that the FSM period is defined as 100 milliseconds using the delay routine. All the other delays are defined as a number of milliseconds divided by the FSM period. And we count the number of FSM periods in the finite state machine to decide if they're done. The reason we define them this way is the amount of time we have to hold the button down to record is 1,000 milliseconds. And even if we change the cycle time, say we changed it from 100 milliseconds to 50, it would still give us the correct RECCNT, the number of cycles to count before we go into record. I always try to do this because I might find later that I need to change my cycle time. I don't want to have to change a whole lot of defines. So it's a pretty straightforward machine. Once again, writing your application code as a finite state machine is a way to make it easy to understand, relatively bug-free, and if it's not bug-free, relatively easy to debug. If something's going wrong in the idle state, you know that it has to be in the code here. If something's going wrong when you record, it's either in one of these record states or it's in the interrupt service. It also makes it very easy to make changes. For example, I originally did not have this erase wait state, and I noticed that when I pressed the button to erase, it would immediately give me the error message that it was already erased. I figured out that the problem was I was going to my idle state up here after I erased, and in my idle state I was noticing that the button was down, it was released before 1 second was up, and that meant I was trying to play, but my recording was erased. So all I had to do was change this state equals from idle to erase wait, add a new erase wait statement that waited until the button was released, and then I went to my init state. I don't go directly to idle here because I want to put up the initial LCD message, which doesn't imply you can play. Normally, if I end playback and I have not erased, I put up a message that says press to play hold to record. But if I've erased, I want to go to the message I use when I initialize everything, which says hold button down to record, because there is no message to play. So once again, I urge you to use finite state machines. They make it much, much easier, not only to understand, but also to make sure your code works right.